So first, let's look at how should we design a validation, because these validation pipelines are the building blocks of success for any model, whether it is simple or complex. So for this, we have to look at a few things. Now, how does validation really play in the model generalization? Okay, we want to do this validation with the view that these models are generic enough. So we take a picture of few teeth. How do we generalize them? How do we know that the model is generic enough, or it's not generic enough that we need to now inject more data to it, maybe augment the model, do whatever we need to do? Okay, so that is the primary goal. So how do we know that validation plays a role in generalization? And then we look at the most fundamental building block strategy, KFold Cross Validation. How to choose K. And very important thing where people stop is they choose K and then they assume everything is okay. But then that is not the truth. A lot of cases, as vanilla KFold fails. And there are solutions to it that we should know so that we use the right ones. And in majority of the cases in production applications, vanilla KFold should not be used. One of those variants should be used, which I will introduce today. All right, so what is the model generalization? So that is the question. So think of it this way. A model, whatever, even if it is an LLM or it could be a random forest, it can be expressed as a mathematical function. Okay. So when these functions are not expressive enough to capture the actual problem, what happens? The models are kind of limited because they are trying to kind of fit to whatever they have seen, and they may not be able to move forward and fit to your production data. This is genuinely the underlying fact which causes what we call as a bias problem. Okay, where the model itself is limited in its ability to know. But what if we became ambitious? We took a lot of data that were noisy, that was from a different domain, we just transported it without too much care. What will happen? In such cases, too much erratic, noisy data gets injected into this model. So this mathematical function then is overly complex. It is trying to kind of fit into way too many things. And when that happens, we call that problem a variance problem, because the model is erratic. It is not stable enough to behave in a certain way. Okay? So that is the variance problem. And this bias and variance problem does exist in every level to every possible model in production or in developments. The matter is about how much we are accepting that they exist, how much we are willing to forego some of the bias and some of the variances for us to productionize things. So there is nothing called 100% bias-free, variance-free problem out there. Okay. So the problem then, if we know that the bias and variances are going to exist, the goal should be to find the sweet spot. Where should bias and variance meet in the spectrum? And this is, we are talking about in the data spectrum. So this is going to be a multidimensional spectrum that we should be able to quantify. And what the generalized models, when we say generalized models, what they really mean is that in some way, based on the various strategies that we are also going to discuss, we have found the sweet spot within the bias variance spectrum so that they behave stable. I mean, their variance is not causing erratic or over complex models. And at the same time, they're intelligent enough, they are not too limited per se. Okay, so that is what we're going to define as generalized models. So now I want you guys to step back and think about various things that you have studied, various models that you have studied, and then keep pondering over the question, how do we find this bias variance spectrum for your own domains and for the various models we have seen? Okay. And another key fact is that a model, if it is generalized, it usually performs well on unseen data. Okay. So that is one, it is taken as one of those examples to understand if a model is generalized enough, if it is put through into production, if it sees some unseen data with certain manageable variances, then it should be able to handle it and absorb it. And this is one of those areas where these larger models, these LLMs that we have studied, plays a very, very important role because they generalize extremely well. And we have capability to make them more and more generalized by using the prompts. Okay, so connected that way. Another important fact here is we can train any model. Okay, A trained model without the generalized learning is going to some way reflect to us when we look at the numbers, the performance numbers, as to how badly or how poorly it is fitting to the training data. Okay. Generally, what we call is the overfitting to the training data is generally called. Underfitting is less mentioned, but the truth is, when you look at the performance numbers without generalization, you're looking at something that is definitely overfitting or underfitting the training data. But what could cause these overfittings? That's another question. Okay, so this is a standard plot you will see, which has got the loss, it's got the iterations, the training iterations. As you go through this, this is how the training losses are going to reflect. But at some point in time, the validation losses just start going in a different trajectory. So this means the validation data is not well performing for this trained model. And somewhere down here is where the trajectory becomes a lot larger. So we mark that territory as a place where overfitting starts happening. Okay, so we have to ask this question: what is this that is causing the overfitting? Because fundamentally, we want to go to the bottom of this problem and solve it. Okay, there are a few perspectives we can take. Okay, the first perspective we'll take is the training data perspective, which is the overfitting happens because the model is too complex for the actual problem. So when we look at it from a training data alone, we can simplify it to state that the overfitting is caused because of model being too complex. Meaning it started fitting too close to the training data, becoming more and more complex as it ran down the iterations. It was trying to find the sweet spot within the weight spectrum, and thus it went on this track, whereas validation loss is poor. When you look at it from a validation data perspective, what we can say is when too much hyperparameter tuning is done, then overfitting does occur. So let us say I found a sweet spot for my model. Okay, and I have found a sweet spot for the model with what condition? With the condition that I have done some hyperparameter tuning on my model. All right. So after doing my hyperparameter tuning, I would have found the sweet spot. But what if I have done excessive hyperparameter tuning to really find that sweet spot? Then in that case, I really have in some way cheated the whole system to make us all believe that overfitting is not an issue. Whereas genuinely, we have done too much hyperparameter tuning. Thus, using the validation data, we have cheated the system to actually overfit. And from a test data perspective, if you look at it, if we were not properly sampling information as we built up our training data set, then again, important test scenarios may not have flown into our training data, which again will cause us to have this problem with overfitting to the inappropriately sampled training data set, and thus the model is poor in performance. This could be overfit or underfit. So let's generalize the term. We are just using the term overfit just to refer to the fact that the model is really not performing well on the outsample data. And we should also care a little bit more about data leakages, which can cause overfitting. So what this means is when you train a model, when you augment models particularly and train them, whether it is CV or NLP or it could be tabular, we have to be carefully considering the fact how some of the features are computed, if there are any sort of common features like people in the tabular space compute means, variances, and medians and stuff, or any sort of a compute that they may have run on the overall data, that should not influence them in cutting this data set into train, validate, and test. Or that should not influence how some of these features are getting populated, let's say in a feature in a validation data set for them to do hyperparameter tuning. So that is a very important thing, that data leakages should be well managed, which is why in the pipeline, you have to care a lot about how your training samples are being sampled from this large population of your overall data. And also how you are carefully choosing this, I shouldn't say carefully choosing, but how you're randomly allocating your validation data set to minimize the bias that you may otherwise have on your training data set. Okay, so you can visualize this for your own use cases, whether it is vision, NLP, or in tabular data space. Visualizing in NLP is probably the most complex. Visualizing in tabular and vision is easier. Okay. Now that we have come this far, let's ask this question. Is there a way we can really solve this overfitting problem or underfitting problem? So we can apply a strategy, a validation strategy, and score the overall system. Then we should be able to manage it. So that is the overall goal of a validation strategy. To be able to score how well we are generalizing as part of the model learn. Okay? So like I said, if we can score it, we can manage it. At the same time, a good validation strategy definitely helps us fail fast, which means if we've chosen a model, we have chosen a training data set and we have done the training, we should be able to come up really fast to say, look, something is off. Things are either overfitting or underfitting much faster rather than waiting till we go into a lot of validation phase, cross validations, and then later on assessing them with test data. So thus we want to fail fast if that is what actually is bound to happen with our existing data and our model choice. And let's start off with a vanilla and a standard cross-validation strategy called the KFold Cross Validation. How does it work? First, it splits the data into K partitions, right? It calls each of the partition to be a fold. Next, it loops in for K iterations. And at each iteration, it is going to take a particular fold or a partition and run it for validation. Okay? Whereas every other partition is being used for the training. So that is the overall purpose. Let's look at an example here. So we take the entire data. We're going to split it into a train and a validate. So when I say entire data, I'm talking about the overall training set. So within the training set, we split them into validation and train. And in the first iteration, we first train the model on this training set, the subset, the small set here, and then we validate it on this. And then we compute whatever measure we want to do. So right now I've just chosen precision. It's a choice I just made, but whatever your measure is, that is fine. Same way you'll do the next iteration. In this second iteration, what are we doing? We are taking a different fold to be the validation fold, and the rest of all the data is the training data. Again, you'll get a precision 77% in this particular case I got, which is much lower than what I saw in the first fold. Now, none of these independently matter so much to us at this phase, but rather we are more interested in running enough folds, enough iterations for us to completely exhaust the data on this strategy. So, okay. So third measure, the third iteration is we again using another fold here, using rest of the data as training and validating on this particular score. And this validated score is the precision score that I've got, which is 92. So already out here, just with the 3, we already see that things are dancing around. 88.7, 77.7, 92.1. Let's do fourth iteration. Fourth iteration, what we have done is we have trained on all the data, but the fourth block, which is the fourth fold here, is the validation fold. And that gives me the poorest precision ever possible. And this is important to note. Fifth one gives me something about 81.9%. Now, what does this mean? We've done some work, KFold cross validation. What are we going to finally do? What do people usually do is they take an overall average on the validation data set's performance, right? So if my precision scores were like this, fold 1, fold 2, fold 3, fold 4, fold 5, they would have said, look, this is my average precision of 80.8%. Yes. But I don't want you guys to stop there. I want you guys to know that fold 4 performed poorly, and that you have to dig deeper into this data set to understand what characteristics of features are bothering your model. Now, this is a generic thing that you can apply whether it's tabular, vision, NLP, it doesn't matter. As long as you have precision scores of various folds, and if you see one of the folds or multiple folds are performing poorly, that means that particular data set has certain characteristics which is not understood or learned by your model. Okay, and that is a place where people generally dig in deeper. This is a place for analysis. We will use this number carefully after looking at all this. Okay, so keep that in mind. Then comes the question. This is all good. We now know where to focus on so that we can dig deeper to bring better data into the model for us to train better. Okay, so that is kind of the gist of what we're taking away. But then again, statistically, this K number, the number of folds we use will drive us either to a success rate or into analysis paralysis space. Okay, so for that we have to make some decisions. How do we decide the K? The goal overall is to have the model estimations, model performance estimation done fairly robustly. That is the key goal. Okay. So what we need is we have to now start connecting of how bias variance starts playing a role when K is chosen. So that is kind of something that we should right now look into or try to understand it. Let us say I choose a K somewhere between 10 and 15. What am I expecting out of this model? I'm saying we need low bias and some acceptable variance. Okay, for us to appreciate this, let's look at a few more examples, then you will know. Let's say I choose a K very low, 4 to 6. When would I do this and why would I do this? Let's question us in that direction. When would I choose K is 15? When would I choose K is 4? I've given the hints here, which is when we need a low bias, I would choose something like this. When the model is suffering with variance, I would choose lower K. Okay, so I've given the answers out, but I want you guys to kind of connect it here, which is, let's say our model is having a large variance problem. How do I even know that there is a variance problem? I would have done some tests with my validation data set, and I would have found data to be something like this. Now, this doesn't have too much of a variance problem, but let's say I had one more of numbers, which is something like 645. Then I would call this particular output to have a variance problem. Okay? Meaning each other fold is on its own. They are not actually coming close to each other from the numbers perspective. That is a variance problem. Okay? What is a bias problem? Most of the numbers are very low. They are not coming near 90% or 80% or 98%, whatever your targets are. All right. So thus, when you're having those problems, we should try to tweak this K in a certain direction to give us a solution. The reason is that internal data of how we're going to use them up for our validation starts to drive that, and that driving factor is K. Okay. So when, let's say my bias is today high, in this model, I wouldn't call the bias to be high. It is average. But still, because I've got 80%, we may think it is high, but that depends on the benchmark we want to have. Let's say my benchmark is 95%. Then in that case, average precision of 80% is too low. I'll say the bias is high. So when I want a lower bias for this, what should I do? I should increase the number of folds. I will push it away from the 5-fold all the way till 15-fold. The reason is then the data is more granularly tested. Model is granularly trained on a smaller data, smaller segments of data, for me to be able to achieve a better bias that is capable for the given model. Okay, so thus, for me to push the bias lower, I have to increase the K. But at the same time, if the model is suffering with variance problems, for me to push the variance low, I have to keep the K low. Okay, so that is the gist of what is written here. But if your goals are different, like for instance, you want to do some stacking and stuff, you will push the K further up. This may sound a bit counterintuitive, but this is done in practice. Okay, many Kaggle competitions where stacking is done, if you see them, they will push their K much higher. Somewhere close to 15 plus to 20, they will take it. All right. If our goal is model hyperparameter tuning, what should we do? Keep it somewhere moderate, 6 to 8. Again, these are tentative, idealistic rule of thumb figures for you to operate with, because now it should open up your perspectives that depending on the goal, your K will change, and depending on that, the overall performances and your perception about the model will start to change. That is the most important thing. And when you have very large data, 250K plus, then don't worry too much about small Ks. Stick with large number of Ks. But the principles you have to understand here is, the larger the Ks are, the model will push itself to reach a low bias, but will have a high variance. The smaller the Ks are, the model may achieve low bias or may not achieve low bias. That is not guaranteed, but it will definitely achieve lower variance. Okay? And when people usually do stacking, they keep it to high numbers. Just keep it there. Because those are key principles for you to remember as you deal with any form of a cross-validation. This is applicable across our spectrum: vision, NLP, tabular data. These numbers will obviously change, but your perception should not be on the number 10 to 15, but rather should be more about relatively understanding that higher the numbers are, lower the biases, lower the numbers are, lower the variances. So thus we have to find a sweet spot between them. A lot of times we learn that KFold is great, but we should also know that KFold is not a Swiss knife for everything. So there are times where we should not use KFold as is. Don't use them, or use them carefully when your target is highly imbalanced. So when your target classes are imbalanced, which is usually the case in production, then you should not use the vanilla KFold. That's what I'm coming to say. I'm going to show you a different KFold to use, but don't use the vanilla KFold, because it fundamentally bulldozes our entire model. It will destroy all the effort we put in and make us believe that our model is pathetic, even though model may actually be good. So be careful when you're running with imbalanced data set. There are times where some of the numeric variables and features carry a lot of importance, and we want to preserve the distribution of them. For instance, when Corona hit on a global scale, people wanted to preserve which sort of ethnics, nationalities were more hit, so that they can do a little bit more study. Whether turmeric powder is really helping Indians have less of some medical issues or not. Okay, I'm just making one example up. So in such cases, obviously, you need to preserve the distribution of those numeric variables. You cannot just slice and dice them as how you want it for you to do some model estimation or trying to understand the KFold results. Same way, there could be numeric data of, let's say, stock market that you don't want to kind of slice and dice them in a certain way, because then it loses its credibility or the whole feature. So be a bit cautious of the fact of what we're dealing with. Next, you may see highly skewed, long tail, leptocritic sort of distributions in your data. Now, how do we even know that these exist? Usually people do pair plottings on their existing tabular data set. So this is very, very tabular data specific, okay? Because the way skewness, kurtosis, and all comes into vision is different. Skewness, kurtosis comes into NLP is different. So let's not go there. For the moment, this third line about high skewness, long tails, leptocritic is more for tabular data, okay? So when you have that, be very cautious that KFold will fail. We cannot use the vanilla KFold. We have to use a different KFold. Or when you have a time series, obviously. KFold knows nothing about time series. So what would it do? It would again do randomly chunk and fold, which may not give us the right results. Similarly, like I said earlier about preserving the distribution of numeric variables, preserving the ordinality of the predictors. So the order, when things orders matter, just like how the time series, it may not even be a time series. In some cases, the ordering matters for your data. In such cases, be careful about KFold. And how are we going to solve these? We are going to actually be choosing a particular KFold solution for each of them, as is given and it's already implemented in SKLearn. So when the target is highly imbalanced, which is the case in many mid-production issues, use the stratified KFold. Because what it does internally is it makes sure that the class imbalance is carried into the KFold, so that when it creates the fold, those folds are also imbalanced in a similar way as much as possible, like the actual underlying data. To preserve the distribution of numeric variables, we use something called as K-bins discretizer, okay? This is a variant of KFold. It's not a pure, just vanilla KFold turned into, but it is something that grew out of the necessity that binning was needed using a smart algorithm, which is, in this particular case, is called the K-bins discretizer. And this algorithm's job is to make sure that it look at distribution of various numerical variables, features going in, and try to build similar distributions as it's trying to kind of make the folds, okay? As it tries to discrete the data. So that is implemented in the K-bins discretizer. So when you want to preserve distribution across multiple features, right, which is important, then what we do is we move to another level of a stratification called the iterative stratification strategy, okay? I'll explain this iterative stratification, but right now understand that it goes into another iterative loop to stratify, which means to selectively pick which sample should be part of a particular bin. And obviously, when you have time series, it's much simpler. You use a time series split. It is not KFold anymore. It is time series split. So thus, your time series is split into different chunks of hopefully meaningful chunks, so that when you make your calculations, whether it is about returns, variances, and various other statistics you calculate, they start making sense. So that gives you the very basic introduction into setting up a validation pipeline. When to use KFold, when not to use KFold, and how we should try to approach the problem using other stratification strategies when you have a particular imbalance in the data, or when you're facing with time series, or when you want to preserve the distribution in your overall feature space.